So there are two different ways that waves can propagate through space. They can either propagate as a transverse wave or a longitudinal wave. Now, a transverse wave is defined to be where the oscillation is perpendicular to the wave direction. That's transverse. So for example, here you have a slinky and it's moving up and down. Well, the wave is moving, has a forward velocity that you can see the wave propagating forward, but the any individual point on the slinky is moving up or down. Now you could also have an oscillation that is left and right, which in this case would be into or out of the screen that you're looking at. That would also be a transverse wave. Up and down, left, right, or at an angle, all of those would be transverse waves because they are perpendicular to the forward motion of the wave. Now, the other type of motion would be where the disturbance is in the same direction or parallel to the forward velocity, and that's longitudinal. So here's an example. You have a compression wave in this slinky. Now, if you were to pick any point, this point would just be moving back and forth in this direction. Well, that oscillation would propagate forward like so. So the disturbance is in the same direction as the velocity. So that would be a longitudinal wave, excuse me. So a good example of a transverse wave would be, say, you go to the ocean and you see some people bobbing up and down as the ocean waves roll onto shore. The waves are moving onto shore, but the people are moving up and down. That's perpendicular. That's a transverse wave. A good example of a longitudinal wave is sound, because sound is just a compression of air. It's a wave or series of compressions and expansions. So there's a good example of a longitudinal wave. Now, how do we find the wave velocity for a transverse wave? We're looking specifically at a string because that's one of the easiest methods to show a transverse wave. The speed of a transverse wave, but specifically here in the string or rope, depends on two things. It depends on the tension of the string, and also it also depends on the mass density. The mass density would be the mass per unit length. Now, compare this to when we talked about fluids, just as a side note. Density of a fluid would be mass per unit volume. It's a three-dimensional density because you're dealing with volume. But here, a rope is very one-dimensional. It only has one direction. And so instead of doing a whole volume, we do per unit length instead. So it's very similar to the density we've already seen, but just different dimensions. Okay, so the speed of a wave in a string or rope depends on tension and the mass density, and the way you can calculate the velocity of a transverse wave would be the square root of tension divided by the mass density. Now here's an example of a sound wave. You have a drum where you hit the drum. There's a membrane on that drum which then oscillates from an extended position to an compressed condition. So the drum membrane vibrates. And as it pushes out, it compresses all of the air in front of it. But as the drum head pulls in, it causes that air to expand. And as a result, you end up with these patterns or series of compressions and expansions of air. In other words, you have a longitudinal wave. This is how sound waves work. Now, how do you calculate the speed of a longitudinal wave? Well, the speed of a longitudinal wave depends on the fluid. And to determine one fluid from another, we're going to use something called the bulk modulus. Perhaps you remember this when we talked about static equilibrium. In your textbook, you can find values for the bulk modulus in Chapter 9. I'm pretty sure that's Table 9-1 in your textbook. And then it also depends on the actual three-dimensional density of the fluid itself as well. And here, if you need those, you can look in Table 10-1, and that's where you are going to see find density values. Now, how do we calculate the velocity of the wave? Well, that's going to be the square root of the bulk modulus divided by the density. Now compare this to what it was for the transverse wave. It's very similar. For the transverse wave, it's square root of tension divided by mass density, or length density. But for a fluid, it is square root of bulk modulus divided by the actual the volume density. Now, there's a specific example of both transverse and longitudinal waves, and that is earthquakes. Earthquakes can produce both longitudinal and transverse waves. If any of you have ever been in an earthquake, not necessarily a fun experience, but if you sit in a room where there's an earthquake and you feel the room swaying side to side, the whole room is all moving together, that would be an example of a transverse earthquake wave. But definitely the more destructive are the longitudinal waves in an earthquake. Why? Remember that longitudinal waves are compressions and expansions. Can you imagine compressing and expanding the foundation to your home? That would cause some very, very serious damage. Now, if this earthquake were to occur offshore, well, you can see that both types of waves do travel through solid material, but only the longitudinal waves themselves can actually propagate through a fluid. That's because fluids have no restoring force. If you look here on the right, this is your longitudinal wave pushing the wave onto the shore. Whereas the transverse wave is going to cause the water to rise and then fall and then rise and then fall, and it just becomes a cycle. It's just a circle. That's all it is. So with an earthquake, longitudinal waves can propagate through water, but transverse waves have to pass through solid matter.